Hello everyone, this is Hussain from North Dakota State University. In this research project, we used bentonite clay as partial replacement of cement, along with some sea-based materials such as sea sand, seawater, and we used coral aggregate as a replacement of natural coarse aggregates. We used sea sand and seawater as partial replacement of natural water and natural fine aggregates. So to analyze the performance of concrete, we used some mechanical performance testing, such as compressive strength at different age of concrete under sulfate attack, under sulfate environment, at 28 days, 56 days, 90 days, and up to 180 days. We performed some microstructural analysis such as XRD, SEM-EDS, FTIR, and TJ analysis, along with some hydration studies to analyze the overall microstructural performance of bentonite reinforced concrete. So here is the mix design that we used in our experiment, in which we used 390 kg per cubic meter of cement and 155 kg of fly ash for the control specimen. And we replaced the cement with bentonite, which was around 39 kg per cubic meter. Same-wise, the sea sand was 84.8 kg per cubic meter, and seawater was 27.25 kgs per cubic meter. Here are some temp images of bentonite clay, cement, and fly ash that we used in our experimental program. So compressive strength, it showed some interesting trend. The control specimen, for the control specimen, the compressive strength for 28 days, it was gradually increasing. However, there was a gradual decrease in compressive strength when the specimen were undergone through the sulfate environment, especially for the concrete specimen, in which the replacement was above 24%. Above 24% means more than 36 to 48%, up to 48% replacement of bentonite and other sea-based materials with the natural ingredients of concrete. So during this analysis, we found that there could be possible 2 to 3 reasons which are responsible for retention of concrete strength. The first reason of retention of the concrete strength, especially at between 12 to 24%, is the aluminum silicate percentage, high percentage in the bentonite clay, which can act which can be beneficial in concrete, making more CSH gel. The second important property of the bentonite clay is the swelling property of bentonite clay. Once it gets in contact with water, the bentonite clay swells, and due to the swelling, it blocks the passage to the external hazardous fluids into the concrete, which can be a reason to retain the overall compressive strength of the concrete. The third and important reason behind to retain the compressive strength of the concrete, especially under sulfate environment for 180 days, is due to the strong cation exchange capacity of bentonite clay. What happens in this process is the bentonite clay arrests the free sulfate ions in the concrete, and it doesn't let it allow to react with the CSH gel and calcium hydroxide of the cement. So these are the 3 reasons which we presume that are the key to retain the overall compressive strength of the concrete. This was one of the important and advanced technique in which, unlikely the MIP analysis, which is common in analyzing the porosity of the concrete, what we did was we studied the porosity of the concrete at 180 days of sulfate attack, in which we put the whole cube of the concrete in a microchromatography chamber, and we studied the porosity. We found that the porosity increased as the replacement of the sea-based materials increased, and also the bentonite clay content increased. We assume that the key reason behind was especially for 36 and 48% cases mixtures. The key reason behind increasing the porosity is like, as the bentonite clay increases, there is a strong capability to retain the water content, and as the percentage of bentonite clay increases, there is less water available for the hydration of the cement. So this could be the reason. That's why at higher dosages, especially after 24%, there was a straight decline in the compressive strength of the concrete, as well as there was in the later slides I will show that there was the ingress of sulfur into the concrete. So here we did the SEM-EDS of the specimen, the control ones, the 12% and 24%. Till 24%, the replacement of the cement with bentonite and other sea-based material was beneficial, as we noticed high content of calcium, silicon, and magnesium. And we presume that this magnesium could be possibly, as the salt that we used in this sulfate attack was magnesium sulfate, but there was magnesium in the rich content of magnesium in the bentonite clay. So we presume that this magnesium is mainly from the bentonite clay, not from the sulfate attack. So there was high content of calcium and silicon and aluminum, which we presume that there is a beneficial effect in making more dense CSH formation. However, after 36%, there was an increase of sulfur content in the mixture, in the cubes. So we presume that after 24%, the ingress of the sulfur was noticed in the concrete, which is mainly due to the unreactivity of the bentonite clay, and because of the retention of the water in the concrete. Another aspect we believe is due to the formation of the secondary attringite needles. This could be also a reason which mostly happens, and it causes the internal cracking. As we can notice, for the 48% of the replacement, the calcium content was sharply declined, which supports our argument, as the compressive strength was also decreased sharply at 48%. Thermogrammetric analysis showed also there were chlorine binding phases like Friedel salts were noticed, but overall we noticed there is a impact on the overall durability of the concrete, as a depletion of carbon hydroxide and destabilization of the CSH under extended sulfate attack. FTIR analysis results also confirm our assumption that as the content of bentonite clay and other sea-based materials increased above 24%, there were phases of sulfate ions especially in 36% and 48% replacement. We also noticed silicate and aluminate phases in the concrete samples, which could be mainly from the unreacted bentonite clay. Heat of hydration shows that for higher dosage mixtures, there was a slow heat of hydration because of the water retention property of the bentonite clay. However, we noticed that for the seawater based concrete, because of the certain minerals present in the seawater, there was an increase in the heat flow. bentonite reaction mechanism in concrete. We think and we believe that bentonite clay can be beneficial in concrete, especially in the regions. For example, we talk about Midwest, where there is a problem of the salts, especially in winter, which can be used. But the dosage should be controlled as the dosage of the bentonite clay increase, it adversely affects the overall performance of the concrete. Because of the swelling, there could be internal stresses, which is yet to figure out, like what is the mechanism of the internal stresses they generate during the expansion of the bentonite clay if they get in contact with water. Conclusions: we found that 24% or below 24% should be considered as optimal dosage replacement of bentonite clay. However, we suggest more trials and more mixes to confirm the suitability of this dosage. But it is we after the experiment, many experiments, we confirmed that above 24% shouldn't be considered as a replacement. The microstructural analysis like SEM-EDS, XRD, and FTIR analysis showed that at higher dosage of the bentonite clay, the presence of sulfate ions were evident in the concrete matrix, which shows that there was the foreign infiltration into the concrete, which could possibly deteriorate the long-term durability of concrete. So we presume for future recommendations, as the bentonite clay based research is limited, as there are not so many literature. I didn't find many research papers on this area, so we suggest that if someone is interested, then it should be considered. The 24% should be considered as upper level as a cement replacement. And we should perform more tests to study and to understand the stress mechanism that is generated during the expansion process, and some durability tests such as ASR should be performed to further confirm the durability aspects of the bentonite clay. In this regard, I highly acknowledge the support of US Department of Transportation that helped us to perform these experiments. Thank you so much.